I'm really excited to be a part of GEW. It's such a great entrepreneurship journey, and we are celebrating the very zeal of entrepreneurship at this global event today. So I'm really excited that you chose me to be a part of this charismatic event. So yeah, let's start with the question and answers. Let's heat up the program and let's find out what we have today. So
welcome to today's Enmarg Immersive Insight webinar. We are so happy to partner with Global Entrepreneurship Week to bring you today's session. Before we begin, we would like to show you a brief video about who we are. Let's get started.
such a huge topic, isn't it? So, to talk about artificial intelligence, first we need to understand what is intelligence. I mean, to a different person, to a different sort of person, the meaning of intelligence differs. But if we totally try to figure it out, dissect it out, it usually could be understood as the ability to make decision. All right, so and it's that ability is based on various patterns, various perspectives and various scenarios. So an intelligent mind is able to basically calculate all those scenario, compute between and make their own perspective, choose their own reliability, and based on all those factors, all those parameters, he takes one decision, and then that decision is, we call it, and maybe an intelligent decision or maybe a stupid decision, but it's on a one-dimensional line of intelligence. Okay, maybe it's very intelligent, maybe it's very stupid, but it's on the same line, whether the IQ is high, whether the IQ is low. So that is in some sort of the definition of intelligence. Artificial intelligence is when we are trying to teach a machine to make those decisions, and machine tries to take those decisions on various perspective. So there are now the world of AI is divided between two sort of intelligence. One is the traditional way of machine learning, where we have to define the models, define that we usually call it as a decision tree. So we have to define that what are the factors which are involved and in what frequency those factors are involved to make a decision. But now there is a new era of artificial intelligence which we are seeing, which is called deep learning, in which the model itself tries to figure out that how many perspective or how many parameters are involved in one decision. So you give it input and give it output. It try to understand the mapping between input and output. It's like looking at the clouds and try to estimate that is it going to be rain or not. It's an intelligent task, and artificial intelligence are doing similar sort of tasks. So it's taking a one input and predicting one output, that is it going to be rain or not.
Over 170 countries are taking part in this today, and we have multiple of people with various events. And this being a lunchtime, we actually have people who are networking right now on Zoom. And even if we don't have enough attendees, it doesn't mean that they're not going to watch it, because the same program is going to be on XRDI. It is going to be on Enmarg as well. We'll be having it on YouTube and with connections to our website. So if you can play our connections and our avenues, yeah, that would be great. So awesome. People will know after the event where to find us again. Okay, we were talking about actually how do you understand what is artificial intelligence, and to demystify the whole thing, he's going to be telling us all about artificial intelligence, which is to and also which virtual reality, augmented reality, all those realities that we're doing in the outer space. It's like as though we have gone back to the 70s and 80s and 90s when we were watching all those Star Treks and space odysseys, and we would think like, is this ever going to happen? I guess we are now living that truth in real life with robotics and humanoids and neural links, and I don't know, he's even talking about artificial brain or electrical brain, right?
Yeah, absolutely.
And understanding the algorithms. So is it only for the science students, or can we also learn something from this presentation today? And maybe we can be inspired by what he has to say today. So
Yeah.
Avi, why don't you take it away and entertain us, educate us, so we can get inspired and know how to get into your space.
Awesome. So, as Rita asked, is it only for science students, or is it only for neuroscience student, or is it only for computer science student? So the answer is it's a very complex computer science, but it's a very beginner neuroscience. And the same thing Elon Musk said about the Neuralink, which is the topic about. Okay, so I'm going to explain the Neuralink in such a way, in such a terms that anybody could understand it without understanding complex terms like backward propagation and all those. So I'm going to make it very easy and going to go with stories that how it's formed and how anyone could understand it basically. So yeah, let's dive into the journey. Let me just make this presentation bigger for you guys so that we can enjoy it better. Thanks for inviting me on this Global Entrepreneur Week USA. So yeah, we are doing this, and we are it's a, as I already said, it's an entrepreneur celebration. So let's start it. So uh, and I also said that Elon Musk said about this technology that it's the state of the art for the engineering, but beginner level science for neuroscience. All right. So this is actually very true when we talk about the engineering in neuroscience. It's for engineers, it's very complex, and understanding the brain is really complex when we, because our challenge is to make machines understand what is the brain doing. Okay, so let me first introduce myself. I'm Avi Dwivedi, and I'm a public speaker for 5 years. I'm a medical imaging scientist. I have worked on medical images, understanding brain anomalies, and all those. So also me, I have this uh, biggest community of India in XR. So XR is augmented reality and virtual reality. So we can definitely talk about AR and VR all day, but I have my own YouTube channel if you want to talk about that or learn more about that. So please do visit. And yeah, so let me also give you some little bit of hints about XR. So XR is, as I already said, India's biggest XR community, and we provide education, and we in fact provide the free education to all the children. So right now we have covered 10,000 plus students in past 1 year. I have a podcast show where 45 plus world leaders in the field of XR has already given attendance and taught our students, and we have learned a lot from them. So we have very great positive reviews, 97 plus positive reviews, 97 plus percentage. We have provided so far 30 plus jobs, networking, and all that. So, but yeah, let's move on this topic, which is generative artificial neural networks, which is GAN, and we are going to talk about neural networks for sure. But this talk is specifically on this the Neuralink brain-computer interface. So the Neuralink is a company which is you can say made by Elon Musk himself, the founder of Tesla, the founder of SpaceX. So he announced this invention where he is going to basically take inputs and from the human brain and going to convert them into signals, and then we can process them, and then we can manipulate them. But let's first understand the technology behind this, which is BCI, means brain computer interface. And it's a very amazing field of computer science which we are going to explore. So in artificial intelligence there is GAN, and then in BCI, brain computer interface, in neuroscience there is the Neuralink. So we are going to dive into these question that what is more powerful, either the brain is more powerful or the computer is more powerful. So to answer this question, why don't we just give some test to a brain and give some test to a computer, and let's find out that which is more powerful. It's a simple task, right? So for example, if we tell you to calculate this number, multiply this by this, so again, it's going to take a lot of time to human to calculate this number, right? Isn't it? And computers are
Sure.
going to do that very, very fast. So definitely computers are powerful, right? But that's not the case. So if you take a look at this video, so here you can definitely see the computer is trying to walk, but he's failing in a simple task which humans are very good with.
That's a good video.
He was trying to open the door, but unfortunately, stairs are very bad for robots right now.
Nice. Yeah. Well, isn't it like computers are what you feed it is? That's what they give you.
Yeah. So
A human being is, has a different kind of, nervous system.
Yep, yep. So to answer this question, we gave a test to humans that calculate this number, and humans failed. And then we gave a different test to robots that can you walk, can you open doors, can you do this, can you do that, which for human is a very minor task, and where robot failed. Okay, so it's very subjective. There are some tasks in which humans are much better, and there are other tasks in which the robots are much better. So now let's try to understand what tasks are they. So let's take a look at the next slide. So turns out the general purpose evaluation means decision making based on various components, various factors, is the task where human is much more powerful. So human has this evolutionary system of neural networks where he has learned so many things, and he has learned the process of decision making. But on the other hand, the specific purpose task, which where the specification is really well defined and well given to a computer, here there the computer is much better. Because humans are not good with uh, following those many instruction or evaluating billions of parameters to make a decision. There humans make a very average decision, and basically takes the intuitions and all the, so there humans fails. So yeah, so it's very subjective that on what perspective you're talking about, right? So in 90 in sorry in 200 years back, so 2 centuries almost, there's a science called phrenology. So in this phrenology, basically it's a science of understanding that in human brain where are all the things stored. So they have given 30 subsections of human mind, divided human mind in 30 subsections, and basically started saying that it's a pseudoscience. It's not true. It's not supposed to true, because they used to dissect humans and try to understand that in what brain foldings, there are a lot of foldings in the brain. So they try to understand in what brain folding, what sort of image is there. All right. So which is illogical, and but let me just come to that. So you can already understand they had this perception that in some section number 16, there must be some hope. In section number 17, there must be some spirituality. In section number E, there must be some sort of love for life and all those things. So they have this sort of 30, 35 subsections divisions, and based on that, this pseudoscience was growing. But then in modern science, we have a similar concept. We have this brain anatomy, and based on the brain anatomy, we have these functionalities. So as you can already see in this color coded map, there are a lot of brain anatomy parts, and we have assigned some sort of functionality. We believe that these functionalities generate from these regions of the brain. For example, the cerebellum are responsible for the motor function. We strongly believe that uh, there are uh, uh, there are temporal lobe which are related to association and all those areas, short-term memory and all those. So there still we believe in these sort of science. All right. So it has no connection, but we still believe that. So now my question is, from where we got this map, all right, or how this map is calculated? And answer to this is this uh, single neuron or single nerve cell. All right. So the very single entity of a brain is basically a single neuron. So this brain is basically communicate to from one part of brain to another part of brain using these electrical signals. The brain is an electrical brain. It's an electrical device. So there is a lot of biology definitely involved, and there's a lot of chemistry definitely involved. That how from the chemicals it actually generates the electrical signal. But the concept is very basic. Is these are called dendroids, and these dendroids, these nodes, are basically responsible for input. So they take some sort of input, which is again an electrical signal, and based on those input, there is some sort of calculation being happening. And after, based on that calculation, from these axons, the output is given. All right. So we can already predict and recreate that particular model in form of mathematics, or in form of concepts, or in form of charts, or anything like that. Okay. So we can also say that there are some inputs x1, x2, and x3, and there are some sort of weights. You can say these nucleus, these mitochondria work as some sort of weights. So, and here are some bias in this particular nucleus. There are some sort of bias, and based on that bias, if the input meets the functionality after multiplying to that weight, if the collective number of input meets the functionality, then we check that if it's crossing the activation function or not. Activation function basically tells if it beyond certain threshold, then fire one, otherwise not fire. All right. So similar thing is happening in this electrical brain. Since there are billions of electrons, since there are billions of you can say nerve cells in a human brain, there are billions of neurons. There are a lot of electrical activity is being going on in human brain. All right, all the time. So also we can sense these electrical activity. So you can imagine electrical activity of brain as this. This is an artistic image. Of course, this is not an original image of your brain, but this is an artistic image that how that electrical activity should look like. The firing neurons are shown as the lit part, and the rest are the dendroids being connected and axons being connected. So axon, dendroids, and the center part, which is nucleus, are very important. Okay, so turns out we can capture this electric activity because there is an electric activity, and we have the method of capturing the electron movement and all those. So we have these electrodes which we can put on the map on the brain, and it has to be put it very precisely, because it has to be the accuracy should be in millimeters. Only then we can totally say that we have mapped these particular areas. For example, this particular node represents through fzp1. All right. So this sort of mapping is being done, and we named each and every point on the head to some sort of map. All right. So these electrodes will pick signals which will come from your firing neuron. So your neuronal firing will be firing, and not just one single neuron will be firing. Certain area of neurons, or certain million neuron will be firing in at one instance. Okay, so certain region
So,
of
so,
neurons.
so
Yeah,
let me ask you, Avi.
sure,
So,
sure.
if I see a bird or something, where will it be firing?
Yeah, that's the understanding, that's the mapping. All right, so I'm going to
Mhm.
cover that as well. For example, if we get this thing as the answer to this is calibration. Okay, we have to first create the map. And how do we create the map? There are two ways of creating map. One, if the map which we want to create does already have some significance, and the other one, if it has no significance. In case it has no significance, we can map it wherever we want, like ASCII code. All right. So ASCII code, in ASCII code, a character has the letter 65. All right. So it has no significance or no logic involved that why a should be 65, but it should be because a map has to be formed. Once we put a on the 65, we can put b on the 66. This is the only logic which we can assume, and so on. But in these sort of cases where already there should be some sort of logic, so the map has to somehow figure out that what logic should be there. All right. So the only possible way of figuring that logic is calibration. So for example, we have to put the subject in some sort of scenario like a fear or something, and then we have to check that which part of the brain or which of these electrodes are getting most amount of signals. All right. So that is that is the objective of these sort of calibrations. So based on those calibrations, once we know that these sort of region are corresponding to fear, or these sort of region are corresponding to love and all those, only then we can check some other patient and say, okay, this area is messy, or this area is not that active that it should be. Okay? So for example, in those EEG, you can see the mapping is being done. The physical area of map is being mapped to these points, and now these points, from these points you can see their FFP is here, and then here is FFP. So these sort of points are getting we are getting the signals in form of these waves. All right. So whenever obviously these x-axis is the time domain, and this y-axis is the frequency domain. So in if the frequency is too high, if the signal frequency is too high, means that area is particularly very active. For example, this P8 is right now working much faster than than FC. So we can exactly precisely tell that which part of brain is right now working more than other. Okay, which part of brain is more active, more sensitive right now. So similarly, here is an example that you can already see this part of area. There are a great amount of uh, intensity in this these sort of frequencies. All right. So this is actually a problem called epilepsy, and epilepsy is also known as the short circuit of brain. As you can already see in this image, it's look so messy. It looks like a short circuit. All right. So epilepsy is already known as a short circuit of brain, so which you can understand. So that is one way of understanding the brain mapping. The other way of understanding brain mapping is a very well-known format and very well-defined format is called fMRI. And there's a lot of research being done, and I'm also investing a lot of time in fMRI research. So I'm really fascinated about this subject. So in fMRI, suppose we put the patient into the MRI machine. This MRI machine is not different from any other normal MRI machine. The functional part is just the subject. So the subject gets a task. For example, subject has to move his right arm. Okay, so subject keep moving his right arm, and he'll be put it in the MRI machine, and we'll check because of the right arm motion which part of brain is being sensitive. All right, so that's how we'll do the mapping of right arm to that particular area which is most sensitive in the brain. So we will say then later that this particular area is responsible for right arm movement, and this particular area is responsible for left arm movement. All right. So that's how the mapping is being done in fMRI. Also, in fMRI, we are figuring out a very cool stuff, which I'll definitely show you in next slides. So that's how the MRI is being measured. You can see it's almost a three-dimensional diagram, and you can see we can also target and notate that particular area which is most sensitive or which is the problematic area. We can definitely see the complete anatomy, and we can find the abnormalities in the fMRI. Okay, so now I'm going to go to next slide and talk about this process. All right, so this fMRI machine returns us these sort of signals, and these sort of signals are in the space and time domain both. All right, since they are in the space and time domain both, we can definitely create a 3D image from these. Important equation in engineering, if you talk about, is called Fourier transformation. So these sort of transformations are being applied to convert from a space domain to time domain and time domain to space domain, and the result of these conversions, these transformation, are these sort of flows. So these sort of flows are being figured out, and we have marked that higher flow frequencies are red, lower are the green, and based on that we have calculated these sort of flow pattern, and we can totally figure out that from where the flow is starting and from where the flow is ending. So we can, that's how we are mapping or checking the activity of the brain. And now I would like to show
My
you
name is
this
Jack
video
Gallant.
for
I'm a
two
professor of
minutes.
psychology and neuroscience here at UC Berkeley, and my lab works on vision. That's our main focus is on the visual system. And vision is a really important thing to work on because humans are very visual animals. And when humans have damage to their visual system, they're really incapacitated. That describes how your brain responds to movies. We want to be able to build a dictionary that will allow us to accurate activity. We want to be able to reconstruct the movie that you saw. We have a brain, and you can see the brain activity is painted here on the
So right now, this is a functional MRI, means the subject is watching this movie and the brain activity is recorded in real time. All right.
side of the brain, but the brain's kind of crunched up in the skull, so it's hard to visualize. So we
And this is the actual projection. The brain mapping is never linear. Okay? Usually the kind of map we see, the kind of map of earth we have seen is a linear map, which means which means Delhi is next to Uttar Pradesh. But in case of brain, it's not necessary that similar belonging or similar senses are next to each other. So it's a non-linear mapping which are being
kind of inflate it and then we flatten it out.
so we train a neural network, we train a convolutional neural network to understand the mapping between the input image, which is this video, and the output generated from this map, which is actually the brain activity of the map, the heat regions of that map.
And we can see a flat map of the visual cortex and the rest of the brain as the person watches the movie. The problem here for
So
us
as the person watches the movie, the subject is having different sort of brain activities, and we are recording that brain activities.
is to translate between these movies that occur and this pattern of brain activity that occurs. And in the study we talked about primary edges, about what the objects are in the brain. Brain activity. Here is the movie, we decode the brain activity.
So since we are activating the brain activity, now we make a generative adversarial neural network, and this neural network is trying to create basically an image out of those brain activity. So the input is going to be the real image and the brain activity, and the output is has to be closer to that particular video. Okay, the input video to the human
in order to reconstruct the movie. So on the left here is the movie we actually showed people, and on the right is our reconstruction.
You can already say some sort of I mean there it's already very hard to predict that what's going to be the output, but we can already see in forms of shapes, in form of colors, we can see the similarities between the output from your brain and the input to your brain.
The movie that we showed has a fairly common object like a person. Our reconstructions are actually fairly accurate. But when the movie that we showed is something rarer, as you'll see in a second, like this abstract thing, then our reconstructions are coarser.
When we are showing a very familiar object, the reconstruction are very accurate, like with the faces, because with the faces human brain has to do a very less work, and with abstract images human brain has to figure out various sort of tricks and abstract image actually is, and this is why it takes more time, it takes more sort of memory, it takes the brain tries to find out and try to match with each sort of memory that what that object could be. For example, a child cannot understand about a snake. If a child is a very small child, he might not able to understand if it's a snake, and he might not able to recognize the snake because he has no memory of the snake. All right. So similarly, if your brain has no memory of that particular object which is there, your brain takes more processing, and the abstract image, it tries to think about the project, and then the reconstructions are not very clear in that case.
I think you'll be able to use this kind of technology or shots at the movie rate of our.
So this research is from 2011, and right now the predictions are much better. The kind of accuracy they got in 2011 is much better now. In 2017, that professor gave a TED talk as well, and that TED talk is very interesting. I'll put the link in the comment. and you guys must check it out. So there are some advantage with EEG, there are some advantage with MRI. They are both very popular techniques of mapping the brain. So fMRI is very great in resolution because we can see a lot of pixels in of a lot of regions. For example, even if we are looking at 1000 pixels, we are looking at 1000 regions of your image, correct, of your brain, sorry. Okay. In this EEG, the frequency is very fast, which means the time which the interval between each frame, each image is very low, but the resolution is very low. Okay. The time is the images are coming very fast, but the resolution time is very low. For example, because the EEG cathode, as I already said, as I already showed you in this one, this one electrode is going to respond for a million neurons, because neurons are so small. These are nerve cells and they are very small. This one electrode is going to represent a million neurons. So this is why the resolution is very small. We can look at a very large area at once. It's like looking at the whole map of Gujarat at once. So that is one problem. All right. But EEG is still in use. So EEG does not have to care about the whole brain at once. EEG looks like this when we care about all the neural activity, all the neural data, when we are interested in all the parts of brain which we want to map. But if we are, for example, trying to map simple inputs like if the person is moving his left hand or right hand, if the person wants to say yes or no, if he's taking an emotional decision or not, so we can only track that particular region, and the amount of electrode what we need reduces to very less. Okay. So here you can see the amount of electrode are less, and this whole helmet could be converted to this device. All right. And as I already said, the Neuralink is not the first device in the BCI market. There are Emotive and there are many other companies which usually have their devices in the consumer market even. So Neuralink has one more addition to this existing market. That is the invasive way. This is maybe the first, not the first, but this is one of the invasive ways. So there are when we don't require a surgery, that is a non-invasive way, and when we require a surgery, that is an invasive method of uh, 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 implanting something. All right. So right now, Neuralink is going to use these sort of robots, and these sort of robots are required because it needed a very precise calculation that where the device should go. All right. So the device itself has a total of 96 threads, 96 wires, and each wire is going to have multiple electrodes. So a total of 3072 electrodes, which means a good amount of resolution is going to be output from your brain, which are going to be recorded. Right. So I have covered a non-invasive way from Facebook. So as I already says, there are non-invasive way possible. So here is an example for Facebook.
The first is electromyography, or EMG, a novel input approach that can read the signals on the motor neurons that run through the wrist to the hand. EMG is still in the research phase, but the Control Labs team that joined us last year is advancing the state of the art rapidly, as we can see in this video. In a
Actually,
sense,
Avi, I did
this
not
is a
understand
brain-computer
this about
interface,
Facebook.
but it's an interface that operates where the
can you
brain
explain this
signals
a
are
little
strong.
bit?
All right. So Facebook does not require a hole in your head. It can simply make you wear a bracelet like this. And these bracelet, as you can see from the inside, has a lot of electrodes. And these electrodes are going to sense the signal which are coming from your brain to your wrist. And based on those signals, it can predict the accurate movement of each of your finger and the precise movement of your hand, even in the cases where you are just willing to move your hand and not actually moving it. It can also predict the will, and based on your intuition of moving your hand, it can move your hand. So as you can see, there is a comparison between the actual hand motion and the motion predicted by this device. So you can see this are the data which are being sent by those electrodes. These lines are the data, and based on that data, this hand is getting an animation sequence. All right, so you can totally see it's following the it's very close to the real hand. All right, so whatever they are trying to do with the Neuralink implant with the invasive ways. The Facebook is trying to do that without making whole and without surgeries. But again, reading from the brain is possible with these sort of implants, all right, without a surgery. But maybe the Neuralink is also trying to write the inputs as well. All right. So, for example, we can also write inputs into someone's head also. For example, the motion from one hand, I can totally transfer the motion from one hand to some other hand, and it's been done over the internet as well. There are being experiments on the monkeys, where the monkey is basically forced to have some sort of connection with some other monkey through the internet, and whatever the sort of motion monkey was moving with his hand, that motion was transferred over the internet to another monkey, and that monkey was moving his hand in such a way that it's his own will. Let me also demonstrate this on humans as well. So on humans somebody did that as well. So let me try if I can find it. Yeah, I am working in this. Yeah, this is the video. This is 5 years back. So they explained on this tech talk. So this
So right
girl
before,
is
what is
being the subject, and the engineer is going to make this implant on her hand, and it does not have to be invasive. It does not have to be inside the hand. All right. So these sort of electrodes are enough to fake that signal from brain. So the hand supposed to feel that signal is coming from the brain, but in reality the signal will come from a machine or maybe from somebody else's brain. Okay, for maybe the brain of that particular scientist. Okay, so that is totally possible. So as you can see, we have to basically give electric flow to these 3 points, and if we can also connect it to some other hand. All right. Okay, so now this guy is going to give a signal to hand, and let's see what will happen. So this is the signal, and whenever the signal, okay, so now it's calibrating. Now basically whenever the girl is making the hand move, we are recording that what sort of signal her brain is producing, because every brain is a little different. For example, every person has a nose, but every nose is a little bit different, right? Similar goes to brain. The anatomy of brain is a little bit different from person to person. So we have to calibrate the machine that what sort of signal her brain generates when it send a message to her hand to move. Okay, so right now the calibration is being done, and once the calibration is being done, he can simply repeat the message, and whenever he will repeat the message, the hand will automatically move.
do you guys want to see some more? All right. Yeah, activity is happening here. We can even click here and try to see one of them. So keep doing it really, really hard. Yeah, so now we've paused on one motor axe potential that's happening right now inside of your brain. Okay. Do you guys want to see some more?
So we can also
That's
calibrate
interesting.
2% and connect 2%. So this person will now control the hand of other person. Okay, so it sounds science fiction, but it's totally possible. So he can control from his brain somebody
Nothing.
else's
Why
brain.
not?
All right.
Because the brain has to do it. Now you do it again. All right, that's perfect. All right. Because the brain has to do it. Now you do it again. All right, that's perfect.
Okay. So this is totally possible. There are ways. Now the problem. Let me talk to you about the problem. What is the problem with that? There are also problem of being hacked with these sort of system. All right. You may ask how. You can be hacked either legally or illegally, both. So what is illegal hack? We already know. What is a legal hack? Are the contracts, some sort of contracts Facebook has with you, some sort of contract your Uber has with you, some sort of contract the Neuralink going to have with you. Okay, that is very known, and we do not read all the terms, or we cannot possibly read all the terms because there are so many, and the language is so technical. It's not possible for a common person to read a contract, right? It's just accept and agree and move to next step. It's always like that, right? So what what Elon Musk could do, imagine that Elon Musk made a deal with Pepsi, okay? And next day, all the people with the Neuralink implant start having this urge to have some Pepsi, okay? And they don't know why they are having this urge of drinking Pepsi, but they are drinking now. So these sort of marketing are called neural marketing, and it's a real thing actually. Okay, so these sort of illegal hacks, maybe legal hacks, could be you could be a target of those as well.
Well, it's the subliminal suggestions that people used to use, even for like product placement or something in
Totally.
advertising used to be used, you know?
Yeah, yep.
Mhm.
If somebody wants to join XRDI, totally free. And if somebody wants to contact me, that is also my links are available, so they can definitely do so. So Rita, did you, I mean, understood what is Neuralink now?
I do. I just didn't know the term. I mean, you know, science is my favorite subject, but then for the last couple of years, I've also been doing entrepreneurship and other stuff. I knew a little bit from reading, but I think you did a very good presentation, very comprehensive, and taking us from the 1800s and down. I think that was an excellent presentation. I mean, you know, actually in India, we used to have brain surgery even 5,000 years ago, which have been documented in the Vedas,
Yeah.
which is to do with Shushruta. And Shushruta in India, they were like doctors who did brain surgery. They did even a lot of surgeries that are now we think are modern, but they were done before, maybe crude, but it's amazing that people lived through those surgeries. I think in a way, I find it more useful when I think about, say, someone is in a vegetative state, kind of semi. Your brain's working, your body is not. And I find those people also can now feel and experience a 3D world and travel around the world. It doesn't have to be a pandemic. It has to be not that, you know, I mean, if I want to go to Louvre, or they can also go to Louvre, and they can also like feel at least something rather than just staring at the TV and without being able to use the remote control or anything. If they can have lenses and things where the mind and the brain waves control what they are wanting to see, you know, I mean, that'll be the next future. And in healthcare, that'll be really helping people, you know?
And
You,
also, I
you
would
get what
like
I'm
to
saying?
add, uh, for the people who are already like vegetative, the technology like fMRI, functional MRI, maybe right now there is no way. I'm not sure. I'm not a neurologist, but right now in a general perception, there's no way to figure out at what extent somebody is vegetative. Are they able to experience but not express? So that is a very big question. And what sort of manipulation is happening in the brain? What sort of chemical disbalance is there already? So we cannot predict that. But with the research of functional MRI, my prediction is in probably the year 2035, we would be able to exactly actually see the dreams of a person in a 2D or 3D display. We can exactly see if somebody is sleeping, what sort of dream he is. We can also see if some people's thought. It can be used obviously in wrong ways, in the right ways, but these are technologies and tools, and I think it depends on the willpower who's using that, how they want to use the ethics and the social understanding of that particular person. But these sort of technologies are definitely useful for that cases.
So I think we have to invite you in our future discussions. And I think I might even have you on a panel discussion with maybe someone who is a neurologist
Yeah.
and people, and we can probably have a brainstorming session and workshop. I mean, I'm very close to the University of Miami, and I'm also involved in their with the research, supporting some of the researchers there, and some of the neurologists and people over there are doing things, fantastic work. And that's why I'm intrigued with this whole world, and I'm kind of the bridge connecting both the worlds. And that is why I have InMark, because I try to, I find that my friends and my contacts are doing such fabulous work, and somehow they don't get to meet. And I love these dialogues, and I think it will probably serve us all, especially when we are sitting in different parts of the world, and we are all doing this global format. And that's why I was telling Avi, it doesn't matter how many people are watching us today, but the discussions that we have is going to be there for all of us to go back to and have a look at. And if you find the right contacts who can actually benefit from this, or feel like, maybe my child wants to know, or a college student wants to know, what are these things, or a mother wants to know, this is where you get all the information that Avi has given us. It's a broad spectrum. And I think it was a very good introduction, Avi. And you have really given us an excellent afternoon and evening, depending on where you are right now. And I will again look forward to having you as a guest. I hope you're available.
Yeah, surely. And I'm always available whenever you need the support from XRDI community. And definitely would love to collaborate in future as well, and would love to invite you on my podcast as well. So it's a beautiful collaboration, and would love to continue this journey. And wish you a very good luck for this initiative GW which you are creating, and InMark. And these are amazing, fascinating initiative which are enabling entrepreneurs to achieve even more, connect even more, build a solid network of connections. So yeah, thanks for enabling us with these platforms.
Thank you so much, Avi. I'll see you on the other side. Thanks everyone for watching, and stay tuned. XRDI and InMark are going to be really bringing you some very good programs in the future, as well as classes. So send us a request what you think you would like to learn about. It's a very interactive way. We also have a Facebook page with InMark, as well as a website. You know how to get through to us and through to Avi with XRDI. So here's wishing you goodbye, and thank you. Bye now.